I hope you can hear me and the screen that I have shared is visible.
Yes.
Okay. Our main goal is to develop fundamental theorem of calculus in the Lebesgue setting. And as a preparation towards it, we collected a few materials and let us recall the following definition that I made in the last lecture, namely the notion of absolute continuity. I should say that absolute continuity is a notion that plays an important role in Lebesgue integration theory, especially when you want to explore the connection between differentiation and Lebesgue integration. Having said that, let me remind you the precise definition of absolute continuity. The notion is close to uniform continuity. And in fact, it's a notion which is something stronger than uniform continuity. Let f is a real or complex valued function defined on an interval. We say that f is absolutely continuous if the following condition is met. For each epsilon greater than 0, there exists a positive delta such that for any finite collection of mutually disjoint intervals ai, bi, inside AB, whose sum of lengths is less than delta, we have correspondingly summation I is equal to 1 to n modulus of f of bi minus f of ai is less than epsilon. So this is the definition for absolute continuity. You have AB on which the function is defined. Corresponding to every epsilon, there exists a delta such that if you take any collection of non-overlapping intervals a1, b1, a2, b2, and so on, an, bn, lying within AB, whose sum of length is less than delta, corresponding deviation in F has sum less than epsilon. So this is the definition for absolute continuity. And we have seen that if you start with an L1 function, Lebesgue integrable function, and find its indefinite integral, then the indefinite integral function is going to be absolutely continuous. If f is in L1, then the indefinite integral capital F of x defined as integral a to x f dm. It's a Lebesgue integral is absolutely continuous. So this result gives you a way to generate absolute continuous function. You can start with an L1 function and you can define its indefinite integral, and that will give you absolutely continuous function. Okay, so these two things we have discussed in the last session. Now, if you recall, in the process of collecting materials for fundamental theorem of calculus, we introduce two important class of function. One is obviously this absolute continuous functions. And before that, I have introduced one more class. Can somebody remind me?
Functions of bounded variation.
Good. So functions of bounded variation. So now you have two different classes of function, absolute continuous functions and bounded variation function. So it is natural to ask whether there is some relation. Okay. So next theorem target to establish relationship between these two class, and obviously this theorem or this result will help us in fundamental theorem of calculus that we are targeting. Okay, so we have the following theorem. Every absolutely continuous function f from AB to K, where K is either R or C, is of bounded variation. Absolute continuity implies bounded variation. Hence, in particular, absolute continuous functions is differentiable almost everywhere. Before going to a detailed proof of this theorem, I would like to see whether that particular part is clear. So assume that we have proved every absolute continuous function is of bounded variation. Then do you see that an absolute continuous function will be differentiable almost everywhere?
Yes, sir.
How does it follow?
Because it is the indefinite integral of the L1 function. Then
No, that we have not proved. Sorry. If you start with an L1 function and you integrate it, then it will be absolutely continuous. We have not proved that every absolute continuous function will be indefinite integral of an L1 function. Is that clear?
yes, sir.
So starting with an L1 function, you can create an absolute continuous function via integration. Till now, we have not proved that every absolute continuous function will be created in that way. Given an absolute continuous function, it will be integral of an L1 function. That we have not proved. In fact, that is a part of fundamental theorem of calculus. So that we have not proved. But please recall the following result, which I have stated, commenting that we will not try to prove it. Proof is too technical using Vitalis covering lemma, etc. Okay. The theorem that I am hinting at is the following. You all know that a monotonically increasing function or monotonically decreasing function for that matter is continuous almost everywhere. That is from real analysis. Do you agree? A monotonic function is continuous almost everywhere. Yes or no?
Yes. Yes.
I have given you a far-reaching extension of this, a theorem by Lebesgue. It is not only that a monotonic function is continuous almost everywhere. In fact, a monotonic function is differentiable almost everywhere. And that is a theorem due to Lebesgue, which I have stated without proof. Can you now remember it?
Yes, sir.
Yeah. So a monotonic function on a closed bounded interval is differentiable almost everywhere on that interval. This we have stated. This is called the Lebesgue theorem. Proof is too technical and lengthy, and hence we avoided it. Okay. Now keep that in mind. Given an absolutely continuous function, the first part of this theorem states that it is of bounded variation. Now, you know what is a characterization of a bounded variation function? What's the form in which a bounded variation function occurs? Can you recall? It is a difference of two
Monotonic function.
monotonic function. And you know that monotone functions are differentiable almost everywhere. Therefore, difference of two monotone functions will be differentiable almost everywhere. Do you agree?
Yes.
Therefore, an absolute continuous function will be of bounded variation if you proved, then it is differentiable almost everywhere is a consequence of previous results that we have already stated. Okay, so that's why I told that the last part as in particular. Okay, anyway, so let us prove the first part, that is an absolute continuous function is of bounded variation. Let's f be a function from ab to k which is absolutely continuous. Of course, we have to prove that it is of bounded variation. For that, you have to prove that total variation is finite. Total variation of function f is finite. But before trying to do that, let us write what is available to us in detail. What is available to us is that f is absolutely continuous. What does it mean? Let us apply the definition. Given any epsilon, I can find a delta and so on. Okay, let us choose epsilon is equal to a fixed number. For every epsilon, you can find a delta, and hence in particular, for epsilon is equal to 1, there is nothing magical about 1. You can take any number. But I don't want to work with epsilon. I want to make it a particular number so that I am taking epsilon is equal to 1. Given epsilon is equal to 1, there exists delta greater than 0 such that for any collection ai, bi. Now let me take xi, yi. I is equal to 1, 2, 3, etc. up to n of non-overlapping intervals in AB, mutually disjoint, I mean, summation yi minus xi less than delta implies summation modulus of f of yi minus f of xi is less than epsilon. This is the definition of where epsilon is 1. This is the definition of absolute continuity. Now we want to prove that f is of bounded variation. As I told, for bounded variation, you have to prove that total variation is finite. What we will do is that the variation corresponding to any arbitrary partition P is bounded by a number that we will prove. Okay, so let us start with an arbitrary partition, but fixed for the time being. Consider a partition P equal to, let us say, A is equal to T0, T1, T2, and so on. Tm is equal to B of the interval AB. What I will prove is that variation of the function f on the interval AB corresponding to this partition P is bounded by a fixed number. And that fixed number does not depend upon the partition P, I will prove. Okay, so that the total variation, which is supremum of all variations, will also be finite. Is that clear? Is that okay?
Yes, sir.
Yeah. Now, in order to see that the variation of f corresponding to this particular partition is bounded above by a fixed number, and that number does not depend upon the partition, what we want to do is the following. What is available is only absolute continuity. And if you want to apply absolute continuity, I need to have partitions or the intervals such that the summation of its length is less than delta. Then only I can apply somehow the absolute continuity. Okay. So for that, I am going to make use of another partition. This is given partition, arbitrary. Now let me choose a partition P dash equal to the points of P are T0, T1. I will call points of P dash as, let us say A1, A2, A3, and so on. I is equal to 0, 1, 2, 3, etc. up to K. Obviously, A0 will be A and AK will be B, and other points are scattered in between A and B. Subset of AB, P, a partition. A0 is equal to A less than A1 less than A2 and so on less than AK, and AK is equal to B. Such that I want to apply absolute continuity somehow. For that I need AI minus 1 I will make less than delta. So I will choose a partition such that the length of each subinterval is less than delta for I is equal to 1, 2, 3, etc. up to K. Okay. Now we shall refine the partition P over which you want to prove that the variation is finite with the help of P dash. Okay. Now consider the combination. You have two partitions of AB. One is P and one is P dash. And P dash is good in the sense that difference of each subinterval is of length less than delta. So in P dash, I can apply absolute continuity. Now you consider the combination of P and P dash, where maybe some few points are repeated in P and P dash. I don't know. In that case, you have to take only once. Okay, the repeated point, where repeated points are taken only once. To put in simple language, I am taking P union P dash. Okay. So what is P? P is the collection Ti is equal to 0 to M. P dash is the collection I is equal to 0 to K. Okay. And now I have P union P dash. Okay. With the understanding that repeated point is taken only once, and I will denote P union P dash as points Si. Okay. I is equal to, let us say, 1 to L or 0 to L, doesn't matter. 0 to L. Okay. So now you have AB and started with the partition P, T0, B is Tm, and in between you have T1, T2, etc. And you choose a partition P dash whose subintervals are of length less than delta. A is equal to A0, A1, A2, so on, AK minus 1, P is equal to AK. And using P and P dash, you constructed a new partition of AB, and the points I have called as S0, S1, so SL minus 1, SL. Keep in mind that SIs are either TI or AI. Okay, after writing it in the arranged manner, it will be either TI or AI. Okay. Now we have, let us consider this sum. Summation I is equal to 1 to M modulus of F of Ti minus F of Ti minus 1, corresponding to the taken partition, original partition P. I want to find sum of the variations in each subinterval, F of Ti minus F of Ti minus 1. Okay. Please remember that SIs constitute a refinement of TIs. Okay. So do you agree that this sum will be less than or equal to summation I is equal to 1 to L modulus of F of Si minus F of Si minus 1? Do you agree? Look at the diagrams. SIs are refinements of TIs. Is
Yes,
that okay?
Yes, sir.
Now what we will do is the right hand quantity summation I equal to 1 to L modulus of F of Si minus F of Si minus 1 we shall compute in a clever manner. Okay. So that we will get a bound for summation I is equal to 1 to M mod F of Ti minus F of Ti minus 1. So look at the right hand side. Now we are going to compute the right hand side sum in a clever manner. So for that, for each I belonging to 1, 2, 3, etc. up to K, okay, let SI1, SI2 and so on SINI be the points from the last partition we formed Si I is equal to 0 to L that lie in AI minus 1 AI. Look at the three pictures that I have drawn there. Look at the last partition, that is P union P dash. The points we called as S1, S2, and so S0, S1, S2, and so on. So somewhere there, you will have definitely AI minus 1 and AI. Because SIs are unions of TIs and AIs. So somewhere there you will have AI minus 1 and AI. And between AI minus 1 and AI, there may be many S that I am grouping. So between AI minus 1 and AI, whatever SIs are there, I am collecting. And they are SI1, SI2, and so on, SINI. Is that okay?
Yes, sir.
Yes.
Now, do you agree that then summation j is equal to 1 to ni modulus of f of sij minus f of sij minus 1? Look at ai minus 1 ai. In between, there may be many SI values, SI points. And now I am summing the deviation corresponding to those SIs between AI minus 1 and AI. This will be less than 1 for each I is equal to 1, 2, 3, etc. up to k. So you have AI minus 1 AI, and in between you have SI1 and so on SINI. I claim that the difference between F calculated at SIs in between AI minus 1 AI will be less than 1. Why is it so?
So it is delta, no?
Everything is inside AI minus 1 AI. Yes or no?
Yeah. Our hypothesis is AI minus 1, AI minus AI minus 1 is less than delta.
Less than delta. And now apply the absolute continuity. Since summation of yi minus xi is less than delta, if you have, not since, if you have, then summation of mod fy minus fxi is less than epsilon. Now look at si inside ai minus 1 ai. Since everything is inside ai minus 1 ai, summation of si1 minus si2 and so on, those sum will be less than ai minus 1. And ai minus 1 is less than delta. And therefore, by absolute continuity, summation mod f of sij minus f of sij minus 1 will be less than 1. So far, so good?
Yes, sir.
Now, go back to what we want to estimate. Therefore, summation I is equal to 1 to m modulus of f of ti minus f of ti minus 1, which is less than or equal to summation I is equal to 1 to L. This is what we had. Modulus of f of si minus f of si minus 1. Okay. Now what we did is we considered ai minus 1 ai, and within ai minus 1 ai, whatever SIs you have, that sum you already computed and it is less than 1. Now what you have to do is do it for each AIs. So this sum will be equal to summation I is equal to 1 to k. Consider ai minus 1 ai, and within that summation j is equal to 1 to ni modulus of f of sij minus f of sij minus 1. Do you agree with this? Instead of counting the entire SI, you count the SIs in AI minus 1 AI and do it for each I. Is that okay?
Yeah, sir.
Yeah. Now this is less than or equal to summation I is equal to 1 to k, and this sum is less than 1. Less than 1. Okay. And hence summation I is equal to 1 to m modulus of f of ti minus f of ti minus 1 is less than or equal to k. K times 1. Okay.
Yes, sir.
Now this is independent of the partition. Partition is p. Partition is p. That's what our chosen partition is. Okay, so this K is independent of the partition P chosen. And what is this? This is variation of the function F over the partition P, corresponding to the partition P over the interval AB. This is less than or equal to K for every partition P.
Yes.
Okay. And since this is true for every partition, VABF, the total variation, is also less than or equal to K, which is a finite number. Okay, so since total variation is finite, F is of bounded variation. That implies F is of bounded variation. So what we proved is that there is some connection between the two classes of function that we have defined, bounded variation and absolute continuity. And the precise connection is that once you have absolute continuity, that will automatically give you bounded variation. Okay. Now that particular part. Suppose F is absolutely continuous. Then in the main part, you have proved that F is of bounded variation. And once it is bounded variation, by Jordan's characterization, F can be written as G1 minus G2, where G1 and G2 are monotone function, monotonically increasing. Jordan's theorem. Now you know that monotone functions are differentiable almost everywhere. Recall that monotone functions are differentiable almost everywhere. This is from Lebesgue theorem. Therefore, F is differentiable almost everywhere. This is an important conclusion that we shall use in future as well. So given an absolutely continuous function, it is differentiable almost everywhere. Okay. Now let me put some remarks. If you see the first part, the main part of the previous theorem, it says that absolute continuity implies bounded variation. Okay. So what is a natural question at this point?
What about the converse?
What about the converse? Whether you have bounded variation implies absolute continuity. Unfortunately, answer is no. Question. F from AB to K is of bounded variation implies, it is a question, okay? Is it imply F is absolutely continuous? The answer is no. And the standard counter example, I will just hint at, because this is not our main aim. If you start digging all these things, we will not reach at our main goal, namely fundamental theorem of calculus. So what I will do is I will just give you the standard counter example that we have for the fact that bounded variation function may not be absolutely continuous, and that counter example serves as counter example for many other things as well. Okay, the example that I am targeting is Cantor's function. You know what is what is Cantor's set? Now we have Cantor's function. Okay, standard counterexample is given by Cantor function. Some people call it Cantor-Lebesgue function. I will just hint at the construction of Cantor function. It is almost similar to construction of Cantor set. Okay, so the construction is closely related to the construction of Cantor set. Let me do as follows. There are many ways to introduce Cantor function. I will do it in the following way. Let us consider function phi1 as follows. Defined as follows. Look at 0, 1. I am going to define a function on 0, 1. That is what phi1 is. Okay. If you remember the Cantor's ternary set construction or the middle third Cantor set, what we do is you divide 0, 1 into 3 equal parts and remove the middle third. And the middle third that you have removed is 1 by 3, 2 by 3, right? There you assume that phi1 has value, let us say half. It's a constant on the removed interval. Let phi1 takes constant value half on 1 by 3, 2 by 3. What is this 1 by 3, 2 by 3? That is removed from first stage, from 0, 1 in the first stage of construction of Cantor set. Now I have to define in the remaining places what is phi1. So this is the axis. You take phi1 to be 0 at 0. Phi1 is 0 at 0 and phi1 of 1 is 1. It's 1. So at 0 it is 0, at 1 it is 1, and on the interval 1 by 3, 1 by 3, it is half. In the rest of the interval, you assume that phi1 is linear. That means I have to join 0, 0, and at 1 by 3 I have defined it as half. That line. Okay, so this is 0, 0, and this is 1, 1. And here you have defined as half, and then you linearly join. Okay. Define phi of 0 is equal to 0, phi of 1 is equal to 1, and linear on remaining subinterval of 0, 1. phi1. I am defining phi1. Is the definition of phi1 clear?
Yes, sir.
Now we are going to do iteratively. Now I am going to define phi2. Okay. Consider phi2. Look at phi2 as follows. Now again I want phi2 a function from 0, 1, closed interval 0, 1 to R. How do I define? Look at 0, 1. In the first stage, you have removed, in the Cantor's set, you have removed 1 by 3, 2 by 3. And in the Cantor's function, what you did is on 1 by 3, 2 by 3, you have defined it as half. So keep it as half here as well, in phi 2 as well. Okay. Now in the second stage of Cantor's set, 0, 1 by 3 would have been divided into 3 equal parts, and you might have removed the middle third. And what is that middle third? 1 by 9, 2 by 9. Am I right?
Yes, sir.
There you define your phi 2 to be the half of 0 and half. That is 1 by 4. 1 by 4. Okay. And what is the next interval that we will remove in the second stage is the middle third of 2 by 3, 1. Am I right? That you will remove in the construction of Cantor's set. And what is it? 2 by 3, 1 middle third is 7 by 9, 8 by 9. Am I right?
Yes, sir.
There, but at 1 you have defined your phi 1 as 1, and at 0 you have defined it as 0. So take the half of half and 1, that is 3 by 4. Okay. So on 1 by 7 by 9, 8 by 9, you have 3 by 4. So in the first stage, 1 by 3, 2 by 3, you have defined as half. In the second stage, whichever interval you removed, that is 1 by 9, 2 by 9, there you define the function as half of 0 and half. And 7 by 9, 9, 7 by 9, 8 by 9, half of half and 1, like that. Okay. Now remaining places, linear. So like this, like this, like this, like this. So I will write phi 2. Phi 2 takes same constant on half on 1 by 3, 2 by 3. This is the first stage which is removed. Okay. But additionally, phi 2 takes constant values. What are the values? 1 by 4 and 3 by 4. 1 by 4 and 3 by 4 that are where it takes 1 by 4 that are removed during second stage of construction of Cantor set. Hope phi 2 is clear. Now you can imagine what will be phi 3. What I will do, I will keep these constant as it is. That is 1 by 3, 2 by 3, I will keep it as half. 1 by 9, 2 by 9, I will keep it as 1 by 4. And 7 by 9, 8 by 9, I will keep it as 3 by 4. Okay. Now look at 0, 1 by 9. In the next stage of Cantor set, you might have removed the middle third of 0, 1 by 9. What is 0, 1 by 9 middle third?
1 by 27, 2 by
1 by
27.
27, 2 by 27. There you take it as constant. Which constant you will take?
1 by 8.
1 by 8. Good. Similarly, the others. Okay. Like that you continue. Okay. So I don't want to write the next stage. Continue this process. Continue this process and obtain a sequence of function phi k. K is equal to 1 to infinity. Do you see that phi 1, phi 2, phi 3 all are continuous?
Yes, sir.
They are.
Obtain phi k, a sequence of continuous function. And also phi k is constant. Where is constant on each open interval removed in the construction of Cantor set that were removed during kth stage of construction of Cantor set. Okay. Now what you can do is that, as I told, I don't want to supply the details. You can see that this sequence of function phi 1, phi 2, phi 3, etc. That sequence is a Cauchy sequence. Where? In which metric space? I don't know whether you are familiar with this metric space or not. Look at this metric space. Collection of all continuous functions defined on 0, 1. The collection of all continuous functions defined on 0, 1. But to talk about Cauchy, etc., you need a metric with the metric usually called submetric. D of elements in C01 are functions. The distance between f and g I will define as supremum of modulus of f of x minus g of x. X is in 01. It's a well-known fact that this metric space C01 along with this metric, I mean submetric, is a complete metric space. Okay. Recall that. It's a good exercise if you are not able to recall it from real analysis. Please try to convince yourself. Recall that C01 with this metric D is a complete metric space. Okay. And you can prove that this phi k that I have defined is a Cauchy sequence. In C01. Once you have a complete metric space and Cauchy sequence, immediately what can you conclude?
Convergent.
It is convergent. So you can talk about the limit function. Okay. Define phi of x as limit of phi kx. In fact, it is uniform limit for every x in 0, 1. So now you got a function phi. This function, limit function, is called Cantor's function. Phi is called. Remember Cantor set construction. That was also a limit. Phi is called Cantor's function. Some people call it Cantor's Lebesgue function. Okay, there is a funny name for it, devil's staircase. Look at the pictures of phi 1 and phi 2. I cannot draw how it phi will look like, but please Google it. There is a nice animation video for how this phi 1, phi 2, phi 3, etc. grows, and finally how phi will look like. Okay, so it will be like a step function. Okay, and it is called devil's staircase function. Okay, you can guess why it is called staircase like. It is called devil's staircase. Of course, whether it is a devil or angel is still debatable, because why it is devil? Because this function is having many property which is counterintuitive, which it's beyond our intuition. And at the same time, it will be like Cantor set, it will be counter example for many facts. Okay. So in that sense, it is an angel. It serves as counter example for many facts. For instance, why I introduced this is that Phi, you can prove that it is bounded variation, but it is not absolute continuous. Again, I will not prove all these things. Phi is of bounded variation. Why it is of bounded variation is very easy, because phi is monotonically increasing. Okay, you can see that phi is increasing, but it is not absolutely continuous. So there are functions which are of bounded variation, but not absolutely continuous. That's why I introduce all these things. But at the same time, let me point out also one more fact about, there are several facts concerning the Cantor function, but let me point out one more fact about Cantor's function. Okay. Please note that this phi is a constant on each of the removed subintervals in the construction of Cantor set. For instance, if x is in 1 by 3, 2 by 3, first middle third that you have removed in the Cantor's construction, what is phi 1 of x on there, on that interval? It is half. Phi 2 of x, you are maintaining that half. Okay, so each phi kx will be half on that interval. Phi k of x is equal to half, and therefore limit k tending to infinity phi k of x also will be half. That is, phi of x would be half. I am talking about in the interval 1 by 3, 2 by 3. Okay, now if you consider, if x is in the second interval, or I can say first interval removed in the second stage, namely 1 by 9, 2 by 9. Okay, then phi 2 of x is 1 by 4. And that will be maintained in phi 3, phi 4, etc. So phi k of x will be 1 by 4 for all k greater than or equal to 2. And therefore limit k tending to infinity phi k of x would be equal to 1 by 4. That is, phi of x would be equal to 1 by 4 on the interval 1 by 9, 2 by 9. Similarly, in the second interval, in the second stage removal, that is x is in 7 by 9, 8 by 9, you have kept phi 2 of x as 3 by 4, and that will be maintained after that. Okay, that will imply phi of x is equal to 3 by 4. So a snapshot of all this discussion is that thus phi, the Cantor function, is constant on each of the removed interval. Do you agree?
Yes.
Yes, sir.
Thus, phi is a constant. I'm not saying same constant, okay? On each of the subinterval removed in the construction of Cantor set. If phi is constant, is it differentiable? I'm talking on of open intervals. Is it differentiable?
Yes, sir.
And what is phi dash?
0.
0. And phi dash of x is equal to 0 for all x removed intervals. Okay, removed intervals I can write 0, 1 minus c, where c is Cantor set. Where c is the Cantor set. Is that okay? Phi is different constant in the removed interval, but anyway, phi dash is 0 on each of the removed interval. That means the complement of the Cantor set, phi dash is 0. Okay. So, but what is Cantor set? You know about measurability and outer measure. What is outer measure of Cantor set?
0.
0. That means phi is differentiable except at a set of measure 0. Right?
Yes, sir.
That is, phi is differentiable almost everywhere. Therefore, since measure of C is equal to 0, we have phi is differentiable almost everywhere on 0, 1. Not only that, at phi dash is equal to 0 almost everywhere on 0. Now, the fact that I want to draw your attention to is the following. Okay, so you have seen that, or at least I have just wrote that phi is bounded variation. That is very easy because of monotonicity, it will follow. And phi is not of absolute continuous. That is bit involved. You can try to do that. Phi is of bounded variation. Phi is not of absolute continuity. Phi is differentiable almost everywhere, and phi dash is 0. Now, what is an implication of this is the following. Now, since phi dash is 0 almost everywhere, okay, I can try to integrate phi dash. What will be the value?
0.
0. You may ask, phi dash is not defined on entire 0, 1. That's okay. If f and g are equal almost everywhere, integral of f is equal to
Integral of C.
integral of g. So phi dash is 0 almost everywhere. Therefore, integral of phi dash it will be 0. So as far as Lebesgue integration is concerned, you don't have to bother whether the function is defined everywhere. It is enough to define almost everywhere. Okay. So integral of phi dash dm is 0. Now what is phi of 1 minus phi of 0? What is phi of 1? How did you define? What is phi 1 of 1?
1.
1, phi 2 of 1 is 1 and so on. Okay, so in the limit it will be 1 and phi of 0 will be 0. So what you observe is that integral 0 to 1 phi dash dm is not equal to phi 1 minus phi 0. This is what we expect in fundamental theorem of calculus. Yes or no?
Yes, sir.
But that doesn't hold. That doesn't hold. The reason for it is that phi is not absolutely continuous. So absolute continuity is the right candidate for expecting such a result. Integral of the derivative will be equal to the difference between the extreme value. Those things you can expect only when the function is absolutely continuous. That is why the absolute continuity plays a major role and so on. We will see. Okay, we will see the results soon. So, but this will example will also serve that you cannot just like that expect integral of phi dash will be equal to phi evaluated in the upper limit minus phi evaluated at the lower limit. You cannot expect it in the Lebesgue integration. Remember, phi is continuous. Phi is continuous. What is not available is absolutely continuous is not available. Okay. Having said that, let us close the discussion of Cantor's function. But those who are interested to learn outside the classroom discussion, I can give you some references. As I told you, since you are going to do project in the next semester, in whatever topic of your own interest, you should develop a habit of reading not only textbook, but also articles. Whereas reading research article is not advised now because it is too early to start with research article. But such things, for instance, I will refer to the following article, which is an expository article. Refer this. A characterization. If you want, I can put it in Teams as well. A characterization of the Cantor function. It's a nice article. Appeared in 1991. It is just 4 pages, I saw. It appeared in American Mathematical Monthly. As I told you several times, this is the good venue where you can start reading articles. Because that is for broad audience with a minimum background. And another one is titled the Cantor function. It's a very long article where lots of properties of Cantor functions are assembled. And it appeared in 2006. It's a long article, as I told. It's 38 pages, 1 to 37. Just talks about various properties of Cantor function. And it appeared in, again, this is another good venue where you can start reading articles. Exposition Mathematica. Anyway, this is for those who want to explore beyond the classroom materials. So let us close the discussion of Cantor set and Cantor function and let us go back to our main goal. So far what we did is that we introduced 2 classes, bounded variation function, absolute continuous function, and we have studied certain properties of absolute continuous function and bounded variation function. Main thing is that absolute continuous functions are of bounded variation. Once it is bounded variation, it will be difference of 2 monotonic function. And please keep in mind that monotonic functions are differentiable almost everywhere. We have accepted it without proof. Okay. So let us continue to gather background material for the main theorem. So we have the following lemma. We shall collect a few more materials. Why I am writing this is otherwise it will be, it will not be clear to you what we are doing. We are just assembling certain definitions, properties, and results that will lead us to fundamental theorem of calculus. So we have the lemma here. Let f is a function from AB to R, not K, AB to R, a monotonically increasing function. If it is a complex value, you cannot talk about monotonic increasing. Monotonically increasing function. Then the lemma says that then f dash, you can talk about f dash because it is monotonically increasing. It is differentiable almost everywhere. And a function need to define only almost everywhere to talk about Lebesgue integration. Okay. Then f dash is Lebesgue integrable. And further, integral a to b f dash dm is less than or equal to fb minus fa. I'm not saying equal to. Is less than or equal to fb minus fa. Okay. Without further delay, let us go for the proof. Proof is simple. First, note that f is monotone. Once it is monotone, you know that it is continuous almost everywhere. In fact, it is differentiable almost everywhere. And once it is continuous almost everywhere, we have stated, or maybe I have proved also, this will be measurable. Okay, a function which is continuous almost everywhere will be measurable. Therefore, f is measurable. Okay, that's one observation. Note that f is monotone increasing. f is a monotonically increasing function and hence measurable. You can even prove directly. I think this is one problem that I have given in the tutorial sheet. Okay, measurability you can see in variety of ways. One is directly using monotonically increasing, or what you can do is, as I told, monotonically increasing will imply continuous almost everywhere, and continuous almost everywhere functions are measurable. Okay. So this I will leave. I will not write the reason. Either you try to prove it directly or use continuity. Okay. Further, by theorem that I have stated, namely Lebesgue theorem, monotone functions are differentiable almost everywhere. Further, by Lebesgue theorem, f dash x exists almost everywhere. Okay. Now let us decipher the meaning of almost everywhere. That means the set on which you cannot talk about f dash is of measure 0. Let E be a subset of AB be such that f dash exists. Then measure of E complement, that is AB minus E, is 0. That will follow from the almost everywhere existence. Is that okay? Are you
Yes,
people
sir.
there? Is that okay?
Yes, sir.
Just I am deciphering the word f dash exists almost everywhere means what. Now define. I want a function which is defined everywhere. Remember, f dash is not defined everywhere. Okay. Now define g of x is equal to f dash x whenever x is in E, and it is 0 when x is in E complement. E complement in AB, I mean. Now you have g on entire AB, and also note that integral of g and integral of f dash will be same. Yes or no?
Yes, sir.
Because g is equal to f dash almost
Everywhere.
everywhere. That's why I don't want to define a function to be on the entire domain to talk about its integration. It is enough to define on a almost everywhere. Okay. Remaining place you define something else, and then this function g, the artificial function that you created, and the original function which is defined almost everywhere will be equal almost everywhere, and hence integral of g will be defined same as integral of f dash. This is why I was telling in Lebesgue integration, I don't bother whether the function is defined on the entire domain. It is enough to define on the almost everywhere. Now, define, now I am going to approximate g. Define gn of x is equal to f of x plus 1 by n minus f of x by 1 by n for each n in n. Okay, there is some issue here, but before going to the issue, what can you say about the limit of gnx as n tending to infinity? Look at the right hand side I defined. It is f of x plus h minus f of x by h. And n tending to infinity is equivalent to h tending to 0. What is that limit actually?
F dash x.
F dash. And you know that f dash exists almost everywhere. Therefore, this gn will converge to f dash. Yes or no?
Yes, sir.
Yes, sir.
Where? Almost everywhere. Almost everywhere. Okay. Now, before that, but if you want to talk about GNX for every x element of AB, suppose x is B, then right hand side involves f of B plus 1 by n. But f is defined only on AB. I don't know what is f at a point after B. But if you want Gn at B, you need f of a point after B. Are you with me?
Yes, sir.
So it is not clear how do I define f at x plus 1 by n if x is b, or in general if x plus 1 by n exceeds b, I don't know how to calculate f of x plus 1 by n. So what I will do is, where this is the assumption we made, we extend f of x is equal to f of b for every x greater than b. F is defined only on AB, but after B, I will keep the F value as F of B itself. Okay, artificially I am extending. Okay, now I have a few observations about Gn. Now, note that first observation, Gn is non-negative. Can you tell me the reason why Gn is non-negative? What is the assumption on F? F is monotonically increasing. So what about f of x plus 1 by n and f of x if you compare? F of x plus 1 by n minus f of x will be
Greater than 0.
greater than or equal to 0. That's why Gn is non-negative. Gn is measurable. Gn is measurable because f is measurable.
Yes, sir.
F is measurable, therefore each Gn is measurable. Now, Gn, know that, please keep in mind that f is differentiable almost everywhere. Once it is differentiable, limit n tending to infinity f of x plus 1 by n minus f of x by 1 by n should coincide with the derivative. Therefore, Gn converges to f dash almost everywhere. And Gn converges to G pointwise almost everywhere, almost all x, because G and f dash are same almost everywhere. Is that okay?
Yes, sir.
Now, from this also you can see that each Gn is measurable, therefore G will be measurable. Once G is measurable, since G coincides with the f dash almost everywhere, f dash will be measurable. Okay. Note that G is measurable. Why G is measurable? Because each Gn is measurable and Gn converges to G. And hence f dash is measurable. So not only that f is measurable, f dash is also measurable. Okay. Why I want measurability? Because you are talking about integral a to b f dash dm. To talk about the integral, first thing that I need is measurability of the function. That's why I convinced myself that it is measurable. Okay, so f dash is measurable and Gn converges to G point-wise. Now I am going to make use of convergence theorem. Gn is converging to G. So integral Gn will converge to integral G if I have suitable hypothesis, either MCT or DCT. If there is no assumption like monotonicity, domination, etc., then I have only one result, namely Fatu's lemma. Okay, so since I don't know whether here it is monotonically increasing, etc., etc., domination also I don't have, so I will resort to Fatu's lemma. By the Fatu's lemma, integral a to b, but I know Gn converges to G, so I don't have to talk about limit infimum. I can talk about G. G dm is less than or equal to limit infimum integral Gn dm. Okay, and look at the right hand side. I'm sorry, left hand side. Integral G will be same as integral f dash because G and f dash are same almost everywhere. That implies integral a to b f dash dm is less than or equal to lim inf integral Gn dm. Okay. Now somehow I have to see that this lim inf appearing in the right hand side will coincide with fb minus fa. Then I am done. because I have to prove that integral f dash is less than or equal to fb minus fa. Okay. So to do that, plug gn. What is gn? This is equal to limit infimum n tending to infinity integral a to b. Though I am writing a to b, I mean the interval ab and I mean the Lebesgue integration. And what is gn? By definition, it is f of x plus 1 by n minus f of x by 1 by n dm. Now apply linearity of integral and so on. This is equal to lim inf n tending to infinity. Okay. 1 by 1 by n is n. N integral a to b f of x plus 1 by n dm minus n times integral a to b f of x dm. Keep in mind that all these things are Lebesgue integral. Okay. And Lebesgue integral is defined ultimately via step function. And integral of step function is defined via measure. Is that okay?
Yes, sir.
Everything ultimately boils down to integration of simple function. And integral of simple function is defined as summation of values taken into measure. Okay. And please keep in mind that measure is translation invariant. Lebesgue measure is translation invariant. Okay. Notice that Lebesgue measure is translation invariant. Why do you want to use this? So measure of AB and measure of A plus 1 by n, B plus 1 by n interval are same. Therefore, I can write this as limit n tending to infinity n times integral A plus 1 by n to B plus 1 by n f of x df. Something like a change in Riemann integration, you will say you put x plus 1 by n is equal to t, right?
Yes, sir.
You put x plus 1 by n equal to a new variable t. Therefore, when x is a, t will change to t a plus 1 by n. When x is b, t will change to b plus 1 by n. You will think like that. But here, what I am using essentially is translation invariant, so that integral over ab of translation of the function f of x plus 1 by n will be same as integral of f, but over the interval a plus 1 by n, b plus 1 by n minus n times integral a to b f of x df. Please look at this change. X plus 1 by n has been now changed to x. And the limit a b is changed to a plus 1 by n, b plus by n. Please don't think it as change of variable now. We have not proved change of variable formula for Lebesgue integral. But how I am doing it is by the translation invariance of measure. Okay. Now this is equal to limit infimum n tending to infinity. Now we are almost done. N times. Now, yeah, you have a plus 1 by n to b plus 1 by n here, and you have from a to b in the subtraction. Now a to b I can write as a to a plus 1 by n and a plus 1 by n to b for large n. I split AB into two, A to A plus 1 by n and A plus 1 by n to B. Is that okay?
Yes. Yes.
And then I can cancel the things and I will get n times integral B to B plus 1 by n f of x dm minus n times integral A to A plus 1 by n f of x dm. First integral, you write it as a plus 1 by n to b and b to 1 plus b to b plus 1 by n. And second integral, you write as a to a plus 1 by n and a plus 1 by n to b with n large. So that two terms will cancel and I will get this. Okay. Essentially, what I am using is Lebesgue integration is additive over the domain. Whole domain can be splitted into two domains, disjoint domains, and then I can do that. Okay. Is that okay?
Yes, sir.
Now, on b plus 1 by n, what is the definition of f of x? Now f is crossed b, and once it crossed b, actually it was defined only up to b. Once it crossed b, I am extending as f of b. So what's the function f of x on b plus 1 by n?
B.
Not b, f of b.
Yes,
Right?
sir.
It's a
FB.
constant, f of
N.
b. So you have integral b to b plus 1 by n, f of b dm. So let me write it. Note that f of x is equal to f of b on b plus 1 by n. So what? So the first integral, if you look, f of x is a constant, and then you will get integral b to b plus 1 by n dm. What is it?
1
You are
by n.
integrating a simple function, 1. Simple function
B
1.
into measure of n.
So it will be measure of b plus 1 by n. And what is measure of b plus 1 by n?
1 by n.
1 by n. And there is an n outside. Right?
Yes, sir.
So that will cancel. So first term will reduce to fb.
FB.
fb. Okay. Now you have lim infimum minus n times and so on. Okay. And that will be written as minus lim sup. Lim sup n tending to infinity n times integral a to a plus 1 by n f of f df. Is that okay?
Yes, sir.
Now f is monotone, and you are looking at the interval a to a plus 1 by n. When x changes from a to a plus 1 by n, f of x will be greater than or equal to f of a because of the monotonicity. Since f is monotonically increasing, what you have is on a plus 1 by n, f of x is greater than or equal to f of a. Do you agree?
Yes, sir.
Therefore, integral a to a plus 1 by n f dm, f of x dm, will be greater than or equal to integral a to a plus 1 by n f of a dm. F of a is a constant, or you can say that you are integrating a simple characteristic function, f of a, simple function, on the interval a plus 1 by n. So what will be that? It will be f of a times measure of that, and measure of the set is 1 by n. So you will have here f of a times 1 by n. Do you agree?
Yes, sir.
Now plug it. Therefore, this is greater than or equal to, but there is a minus. So it will become ultimately less than or equal to. Integral a to b f dash dm is less than or equal to, first term is fb minus second term is greater than or equal to this. Right? N will cancel. There is an n here, and that n will cancel. Since it is greater than or equal to with a minus, it will be less than or equal to minus fa. Do you agree?
Yes,
Yes,
sir.
sir.
And this proves the result. The lemma. Integral of f dash is not equal to, less than or equal to fb minus fa. That too with the hypothesis that f is monotonically increasing function. And f dash. And this automatically will give you that f dash is in L1. This fb minus fa is a finite quantity anyway. Okay. Now we are ready to state and prove fundamental theorem of calculus. Unfortunately, today also we cannot see the proof. Okay. But let me at least state fundamental theorem of calculus in the Lebesgue setting. So I will say part 1 or version 1. Part 2 also is there. So let me at least state part 1. But for part 1, most of the things we are almost done. Let f is in, I am starting with an L1 function. Suppose I have f in L1. Now, what do you know about its indefinite integral capital F of x? Once a function is in L1, its indefinite integral will be
Absolute continuous.
define capital F of x is equal to integral a to s small f df for every x in AP. Then the theorem says that then capital F is absolutely continuous. That we already saw. Once it is absolutely continuous, it is of bounded variation and hence it is differentiable almost everywhere. And it is differentiable almost everywhere. So this is also not new to you. Once it is differentiable almost everywhere, at those points where it is differentiable, you can talk about derivative. And the main part of the theorem is this. Further, capital F dash x at points where f is different, capital F is differentiable, you can talk about f dash. F dash x will be equal to, what's your expectation? How did you get capital F? By integrating small f. So if you differentiate, what you should get?
fx.
Small fx.
F itself.
X for almost all x. Almost everywhere. X in AP. So this is the fundamental theorem, first version. Okay. So it talks about the derivative of an integral. Derivative of the integral is same as the integral. Roughly with all the hypotheses. Okay. The function should be L1. Okay, then you have, and derivative when I talk, it is not derivative everywhere, derivative almost everywhere. I can talk about derivative only at almost all points on AP. So this theorem is proved almost. What is the only part remaining? I am talking about the proof. Suppose now you want to prove this theorem. Which part is remaining to prove? F is absolutely continuous, you have already seen, right?
Yes, sir.
It is differentiable almost everywhere. Once it is absolutely continuous, it is differentiable almost everywhere also you have seen. So what is the main content of the theorem is, what is its derivative? That is capital F dash x will be same as small f of x. This is the main part to prove. Remaining things we have proved. So let me start the proof. We already observed that capital F is absolutely continuous. And hence differentiable almost everywhere. So half of the theorem we have already proved using various lemma, etc. Differentiable almost everywhere. What remains is to prove that capital F dash of x coincide with small f of x wherever you can talk about the derivative for almost everywhere on AP. Okay. Since it is already time up, I will not venture to start the proof. This is what we have to prove. Okay, I will divide into 1 or 2 steps and do that. Since we have already collected all the materials, proof will not be difficult. Though it is not very short, it will be again lengthy. We shall use all the theorems, proofs, lemma, etc. we have collected. Okay, so I will stop here.